Hello everybody, I'm back again. We're going to be looking at section 5.2 now in Reif, and in this particular section, Reif decides to show us how one can calculate specific heats, namely the molar specific heats with constant pressure and constant volume. Now, the way we dissect this particular problem is that we start with our first law of thermodynamics, stating that our change in heat is equal to our change in energy plus some change in our work. Reif has already decided to just write our change in work in terms of pressure and volume because that allows us to make a connection to the ideal gas law in this particular instance. So quick substitutions can be made with that respect. So we begin this section by first looking at our molar specific heat with constant volume, CV. Now, at a constant volume, we write our first law of thermodynamics, expressing our heat in terms of our change in energy and our change in volume. And because we want to keep volume constant, dV obviously has to go to 0, right? Leaving us with the fact that our energy is just equal to our change in heat. So we define our heat capacity with constant volume as a change in temperature per mole, or a change in heat rather, per mole of gas, where we have our partial derivative of our heat Q with respect to our temperature per mole nu with volume constant is equal to our molar specific heat with constant volume. We can also alternatively express this as a partial of E with respect to T with constant volume, which comes in handy whenever we are calculating or showing some expressions of how our specific heat is actually related to that energy. If we remember from last time, we were able to express our change in energy as this differential, particularly whenever we write it as a function of volume and temperature. But as we showed both experimentally with Joule's experiment and with the proof in 5.1, it really doesn't depend on volume at all. So we can just say that this part goes to 0 for an ideal gas, which just leaves us with that our change in energy is equal to our partial change in energy with respect to temperature at constant volume times some small change in our volume, right? So now we can begin to try and connect these dots. Since we know what our dE is and we know how to express C sub V, we can move some terms around. Namely, we can get our partial derivative of our energy with respect to temperature all by itself by multiplying both sides by the number of moles in our substance. We know that our partial derivative of our energy with respect to temperature with constant volume is directly equal to our derivative of E with respect to temperature. So with that in mind, we can make a direct substitution from here to here, right, using this. And then we can just multiply both sides by dt to get dE by itself. And what we show is that our small change in energy E is equal to our change in energy temperature times the number of moles of substance we have in our ideal gas times its specific heat capacity, right? This kind of echoes the whole similar form of, oh my goodness, if this pen would write, that'd be swell. Q equals M C delta T from some of our other calculations, right? So that's what that would echo in that case. Similarly, we can use a similar or nearly identical procedure in order to get our molar specific heat with constant pressure. We start out once again from the first law, and we make our substitutions that we have last time and from the ideal gas law. Namely, we substitute dE with our newfound relation of nu times C sub V times our delta T, plus work is being re-expressed in terms of pressure and change in volume. And from our ideal gas law, we can relate a small change in volume with a small change in temperature, and then just do some algebra, get P by itself, and then substitute that value back over here, right? Now, our change in heat with respect to temperature at a constant pressure is what our heat capacity with a constant pressure looks like instead. So over here we have dq over dt with constant volume is equal to CV. The only difference with this one is that we hold instead our volume constant, we hold our pressure constant, which I forgot to denote down here. There we go. Pardon the chicken scratch. But yeah, the only difference is that we're holding pressure constant instead of our volume constant. And then we can verify this relationship by actually going and calculating the inexact differential of dq. We basically just take our derivative of q and we evaluate that, and we get that it's equal to nu times c sub v plus our number of moles of our substance nu times the ideal gas constant r, and then we just divide the whole thing by 1 over nu, and we actually recover the fact that our molar specific heat with constant pressure is equal to our molar specific heat with constant volume plus our ideal gas constant. What this actually shows us is, algebraically speaking, if we're doing some sort of calculation, our molar specific heat with a constant pressure will always be more than our molar specific heat with constant volume. That's another very important thing that we can derive. And also, secondly, another thing we can derive is this ratio between these two constants being what we call gamma. Gamma describes the ratio specifically between the molar specific heat of constant pressure over the molar specific heat of volume of any sort of given substance. And then this, once we actually do the algebra, ends up being 1 plus R over molar specific heat with constant volume CV. That's what we can get from there. So all in all, in order to derive these particular terms, all we do is that we start off with both the first law of thermodynamics and our ideal gas law, and then using our knowledge of differential equations, we can rewrite our total derivatives instead in terms of our partial derivatives times some smaller change, and then just make our proper substitutions, and we are able to algebraically derive values for what our molar specific heats are, and how they're related to one another, and how they're related to changes in heat, and how they're related to changes in energy.